On August 2018, the world of mathematics convened in Rio de Janeiro. It was the first time the International Congress of Mathematicians, the largest gathering of its kind, had ever been held in the Southern Hemisphere. Every 4 years at this event, the community honors its best with the Fields Medal, the highest honor in mathematics. The Fields Medal is often compared to the Nobel Prize, but it is even more exclusive. Given only every 4 years to mathematicians aged 40 or younger, it requires not just groundbreaking work, but also the potential for a rising career. The strict age limit and infrequent awards make it highly coveted and symbolize a unique recognition of youthful brilliance at the height of mathematical achievement. One of the names announced that day was Alessio Figalli for his contributions to the theory of optimal transport and its application to partial differential equations, metric geometry, and probability. Figalli had won for his mastery of a problem that is at once ancient and utterly modern, finding the most efficient way to move something from a starting configuration to an ending one. It is a question that describes everything from the logistics of a city, the formation of crystals, and the movement of clouds across the sky. His journey to that stage, from a childhood in Rome to the pinnacle of his profession, is the story of a mind uniquely suited to finding the best path, not just in mathematics, but in life. Alessio Figalli was born in Rome on April 2, 1984, into a family where both the scientific and humanistic traditions were part of everyday life. His father was a professor of engineering, a man of numbers and structures. His mother was a teacher of Latin and Greek at a classical high school, a woman of language and history. From this dual inheritance, a particular kind of mind emerged. Even as a child, Figalli's defining characteristic was a drive for efficiency. He recalls that he always finished his homework first, so that he could enjoy his playtime without distraction. For me, it was always a balance between how good a grade I could get and how much time I had to spend to get such a grade, he said. I was always an optimizer. I wanted the best for the least effort. Mathematics came easily to him, but it was not his passion. His interests were those of any other Italian boy his age: soccer, cartoons, and friends. When the time came at age 13 to choose a high school, he did not select a scientific track. He enrolled in a Liceo Classico, a classical high school, immersing himself in philosophy, Latin, and ancient Greek. The choice was rooted in a common Italian belief that a classical education provides the broadest possible foundation, leaving all future doors open. He found some of it interesting, but much of it a bit boring. Sports remained his great interest, and he was not a prodigy preparing for a mathematical destiny. The turning point happened during his third year of high school, when a mathematician and his father's colleague encouraged him to join the Mathematical Olympiad. He called this experience an illumination. For the very first time, he started to truly understand mathematics, not just as a bunch of dry rules to remember for tests, but as something dynamic and exciting, a way to really dig into problems and figure them out. At the Olympiad, he met other teenagers who spoke of mathematics with a similar excitement, and they all spoke of one place, the Scuola Normale Superiore in Pisa, SNS. Founded by Napoleon in 1810 as a branch of the Parisian École Normale Supérieure, the SNS is one of Italy's most prestigious and exclusive institutions of higher learning. Admission is based solely on merit, and for the few who pass the grueling entrance exams, tuition, room, and board are all free. Driven by this fresh goal, Figalli hit the books, acing the math and physics needed for the exam. Even though he made it in, getting to that famous university was a huge surprise for him. He was surrounded by Italy's smartest young scientists, and most of them came from special science high schools. Figalli, with his traditional education, didn't even know what a derivative was, a super basic idea in calculus and how physics is explained. That was a big hurdle, and it made his first year a real struggle. Yet his optimizer's mind saw the most efficient path forward. He did not skip classes. He did all the exercises. He was, he admits, an exemplary student. His classical education, while leaving him behind in technical knowledge, had trained him in logic and methodical argumentation. His lack of prior exposure meant that every concept was new and exciting. Within a year, he had caught up. The next year, he picked up a highly technical work by Luigi Ambrosio, a leading mathematician at the school. Less than a week later, he appeared in Ambrosio's office, having fully understood it. Ambrosio was stunned. The boy who had arrived without knowing calculus was now on the verge of a remarkable research career. The body of work that won Alessio Figalli the Fields Medal is centered on a theory that sounds simple. It's called optimal transport. It is the search for the most efficient way to move a distribution of something from one state to another. However, this straightforward idea has turned out to be one of the most powerful and unifying concepts in modern mathematics, and Figalli is one of its masters. The question of optimal transport is nearly as old as the industrial age. It was first formally stated in the 1780s by the French mathematician Gaspard Monge, who was tasked by the military with a very practical problem: how to move a large quantity of soil from an excavation to an embankment with the least amount of effort. Monge's work was to find a transport map that minimized the total distance traveled. For nearly 150 years, the theory remained confined to mathematical echelons. It was revived in the 1940s by the Soviet mathematician and economist Leonid Kantorovich, who saw its immense economic potential. Kantorovich broadened the problem to address complex logistical challenges, like allocating resources from multiple sources to multiple destinations to minimize cost. For this work, he was awarded the 1975 Nobel Memorial Prize in Economic Sciences. Let's take the example of bakeries and coffee shops in a city. Let us say our goal is to find the best possible arrangement for the entire city, ensuring that all the croissants from all the bakeries are delivered to all the coffee shops that need them with the minimum total transportation cost for the system as a whole. What makes the problem so complex is that the system must be optimized globally. A decision made by one bakery affects every other bakery and coffee shop. At its heart, optimal transport provides a way to measure the distance or cost between two different arrangements of material. Imagine two photographs. Optimal transport can be thought of as a way to calculate the cost of transforming the first picture into the second by measuring the effort required to move every pixel from its starting position to its final one. To solve such a problem, mathematicians need a set of rules that govern the most efficient paths. These rules are contained within a special class of equations known as partial differential equations, or PDEs. A PDE is an equation that describes how a quantity changes over space and time. The heat equation, for example, is a PDE that describes how temperature spreads through a metal rod. The wave equation is a PDE that describes the vibration of a guitar string. The specific PDE that often governs optimal transport is called the Monge-Ampere equation. It is a notoriously difficult nonlinear equation, first studied by Monge and André-Marie Ampere 2 centuries ago. For decades, the structure of its solutions remained unknown. A major breakthrough came from Figalli's work with his collaborator Guido de Philippis. They established a new understanding of the regularity of these solutions, essentially proving that the maps generated by the equation are much smoother and better behaved than was previously known. This work provided a key that unlocked a new range of applications for the theory. The true power of Figalli's work lies in its ability to connect this abstract mathematical world to the physical one. One of the most elegant applications of his work is in understanding the shape of crystals. Crystals, like soap bubbles, naturally arrange their atoms into shapes that minimize their surface energy. But what happens when you apply external energy, for example, by heating a crystal? The change in shape becomes an optimal transport problem, where each particle moves to its new position along the most energy-efficient path. The same mathematics describes the movement of clouds. The vast collections of water particles that make up a cloud shift from one configuration to another by following paths of least resistance, an optimization process hidden within the seemingly random churning of the atmosphere. This was a problem that intrigued him for 7 years before he and his collaborators finally solved it. Figalli has also made major contributions to free boundary problems. To see what this is, think ice melting in water. The free boundary is the constantly shifting, unpredictable interface between the solid ice and the liquid water. His work helps to describe the geometry of this boundary and how it evolves. After earning his doctorate in 2007, under the joint supervision of Luigi Ambrosio in Pisa and Cedric Villani in Lyon, the latter himself a 2010 Fields medalist, he embarked on a career that took him across Europe and to the United States. In 2009, at the age of 25, he moved to the University of Texas at Austin, where he would spend the next 7 years. In Austin, he worked closely with Luis Caffarelli, an Argentine-American mathematician widely regarded as the world's leading expert on partial differential equations. Figalli calls Caffarelli one of his mathematical heroes. His work brought a steady stream of accolades long before the Fields Medal, including the Stampacchia Medal in 2015 and the Filtrinelli Prize in 2017. In 2016, he returned to Europe to take up a chaired professorship at ETH Zurich, one of the world's premier technical universities, and in 2019 he was appointed director of its Institute for Mathematical Research, FIM. Today, his research continues to push into new territory, most notably the application of optimal transport to machine learning. From a theoretical viewpoint, machine learning is an optimization problem, where a system's parameters are adjusted to perform tasks like classifying images. Figalli is exploring how optimal transport can make these systems more stable and reliable. A central challenge is what is known as the curse of dimensionality. As the number of features an AI model must consider increases, the complexity of the problem grows exponentially, making it computationally intractable. To address this, Figalli and others are developing a new approach. The idea is to reduce a high-dimensional problem to a series of simpler, lower-dimensional ones. The process is analogous to understanding a three-dimensional object from its two-dimensional projections. By taking many X-rays from different angles, one can reconstruct the full object. Similarly, by projecting a complex, high-dimensional problem onto many simple one-dimensional lines, solving it there and then gluing the results back together, it may be possible to find a solution to a problem that was once impossibly complex. Throughout his peripatetic career, Figalli has maintained a life beyond mathematics. He is married to Michela Jacobelli, a fellow Italian mathematician whose work focuses on kinetic theory and partial differential equations. For years, they managed the difficult logistics of a two-career academic couple, with Figalli in Zurich and Jacobelli at Durham University in the UK. After getting his Fields Medal, he joked how there is one problem I really hope to solve soon. That is me and my wife living in the same city. That problem now appears solved. For the 2024 to 25 academic year, both Figalli and Jacobelli have been selected as members of the prestigious Institute for Advanced Study in Princeton. Figalli is not resting. The Fields Medal, he says, is an encouragement to keep going. He sees a landscape of unsolved problems stretching out before him. For every problem that you solve, there are at least 5 that you cannot solve, especially with difficult problems, he has said. I think I have work for the next 30 to 40 years, and I am not scared of this. The optimizer's path does not end. For a mind like his, the search for the best of all possible worlds is a journey without a final destination, a continuous exploration of the beautiful, orderly, and often surprising language of nature.